GCE Advanced Level Chemistry Practical number 13, Identification of Halide Ions. Aim of this practical is to develop skills of identifying chloride, bromide and iodide ions. In this practical, we will be using silver nitrate solutions to identify halide ions, lead nitrate or lead acetate to identify halide ions, chlorine water and carbon tetrachloride to identify halide ions, and finally we will be using concentrated sulfuric acid to identify chlorides, bromides and iodide ions when they are separately present in solutions. So without further ado, let's move on to the reagents we need to carry this practical. To carry out this experiment, these are the reagents that you would need. We would be using sodium chloride solution, which is made out of sodium chloride solid. As you can see, it's a white color solid. We'll be using sodium bromide. Again, in front of it is the white color solid that we use to make this solution. We'll be using potassium iodide. Again, potassium iodide solid is in front of the solution, which is a white color solid. Apart from that, we'll be using dilute ammonia, concentrated ammonia, chlorine water. We'll be using carbon tetrachloride, CCl4. We'll be using dilute nitric acid, silver nitrate solution, a lead nitrate solution. So in the practical, we will be able to use lead acetate or lead nitrate solution. In this case, we have actually chosen to use lead nitrate. We'll be using concentrated sulfuric acid as well as a little bit of starch. Using this starch, we'll be making a starch solution later in the practical. Apart from that, apart from the reagents that we'll be using for this practical, we'll also be using some equipment such as test tubes and a wash bottle containing distilled water. Now, let's move on to the experiment. First, we'll be starting with how halide ions react with silver nitrate. Initially, we'll be taking sodium chloride, which will bring in chloride ions into the medium, and we'll be reacting it with silver nitrate, and we'll be observing the changes that take place. So let's take a little bit of sodium chloride solution and transfer it into a test tube. So in the sodium chloride solution, you will have sodium ions and chloride ions. We are testing for the chloride ions in this solution. After transferring small amount of sodium chloride, I will now add a little bit of silver nitrate. Now, silver nitrate will contain silver plus ions and nitrate ions. So when silver ions come into contact with the chloride ions, we will see what happens. As you can see, when you react silver nitrate with sodium chloride, you will be forming a white color precipitate. This entire solution now appears white as a result of formation of a fine precipitate that is silver chloride. If you let it stand for a while, you will see the precipitate sedimenting at the bottom, leaving the supernatant on the top. So this is silver chloride that is produced, which is white in color. So now we will take a portion of this silver chloride precipitate and transfer it into a different test tube. So I'll be transferring a little bit of this silver chloride suspension, I would say, into a different test tube. And then we will add a little bit of nitric acid and a little bit of dilute ammonia to see what kind of changes we can observe. So to the first test tube, I will do nothing. We'll keep it as our control to compare it with the results we get. To the second one, I'll be adding a little bit of dilute nitric acid. So to this silver chloride precipitate, I'll now be adding a little bit of dilute nitric acid. We'll give it a little swirl. As you can see, addition of nitric acid to silver chloride solid did nothing. It did not bring about any chemical change because silver chloride does not dissolve in nitric acid. Then we will take the remainder of the suspension, where we have silver chloride here, and we will add a little bit of dilute ammonia to see if dilute ammonia will be able to dissolve the silver chloride precipitate that we have here. As you can see, without even giving it a swirl, you can see the precipitate is starting to dissolve. Now let me give it a little shake. You can see the precipitate is starting to dissolve. Since we have a lot of precipitate, it takes a lot of ammonia or dilute ammonia to dissolve it, and it takes a little while. So we'll give it a little while until everything is dissolved. I'll have to add a little bit more dilute ammonia. Now you'll be able to see an almost clear solution because the dilute ammonia was able to dissolve the silver chloride solid that was present in this test tube. So with this, now you can see a nice comparison where we started with mixing sodium chloride and silver nitrate, and we produced a precipitate, silver chloride. We'll add a little bit more water to see the precipitate a little bit more clearly. You can see at the bottom of this test tube, there is silver chloride solid formed. And then we took a little bit of that silver chloride precipitate and reacted it with nitric acid. We did not observe any change. That is because nitric acid does not dissolve silver chloride. And then later on, we took a little bit of silver chloride solid and reacted with dilute ammonia. Dilute ammonia, as well as concentrated ammonia, is capable of dissolving silver chloride solid. You can see a completely clear solution here because all of the silver chloride has been dissolved in the presence of dilute ammonia. So that are the reactions that we can do with chloride ions and silver nitrate. Now, let's move on to bromide ions. Let's take a look at how sodium bromide will react with silver nitrate. So, to introduce bromide ions, we have taken sodium bromide solution over here. So, we'll take a little bit of sodium bromide into a test tube, like so. And into this sodium bromide solution, we will add a little bit of silver nitrate. Silver nitrate solution will introduce silver ions into the medium. As you can see, as soon as I put a little bit of silver nitrate into the test tube, it will react with the bromide ions in the solution and will form a pale yellow precipitate. Now this is silver bromide. We'll mix it together quite well. You can see the precipitate that is formed over here is a pale yellow color. We'll compare the colors later on to silver chloride, silver bromide, and silver iodide. But in this case, you can see the precipitate that is formed is going to be a pale yellow color. It is quite difficult to properly distinguish it from white color. But if you compare it against silver chloride, you will very clearly see that this is a pale yellow color. Right, so we will dilute this suspension of silver bromide a little bit further. After diluting it a little bit, now this is silver bromide solid particle suspended in aqueous solution. We'll be separating it into two other test tubes. Right. After separating it into two other test tubes, now we have three test tubes containing silver bromide. Now, to two of these test tubes, we will add dilute nitric acid to see it can dissolve silver bromide, and we'll be adding concentrated ammonia to see if we can dissolve silver bromide. So, first of all, we'll take a little bit of dilute nitric acid, and we'll take silver bromide suspension, and we will add dilute nitric acid to see if there will be any observable change in the medium. As you can see, adding dilute nitric acid did not bring about any change. This is because dilute nitric acid is not capable of dissolving silver bromide solid. We would be moving on to adding a little bit of ammonia onto this. Dilute ammonia is actually not capable of dissolving silver bromide, so we'll be straight away adding concentrated ammonia to see if that is capable of dissolving the silver bromide suspension that we have over here. We have to take concentrated ammonia for this, so we'll take a little bit of concentrated ammonia solution. Upon addition of concentrated ammonia, you can see the solid starting to dissolve. Without even shaking it, the solid has started to dissolve, and now if I give it a little swirl, you will see all of the solid that was present over here is now dissolving in concentrated ammonia. So silver bromide is soluble in concentrated ammonia. We'll add a little bit more just to make sure that every particle here is completely dissolved. Right. So we'll leave it aside for a while, and then we'll move on to the summary of what we learned here. When mixing bromide ions with silver ions, you will form a precipitate which is pale yellow in color, known as silver bromide, AgBr. It is pale yellow in color. We took a portion of that precipitate and reacted it with a little bit of dilute nitric acid, and we saw dilute nitric acid could not bring about any change, as dilute nitric acid is not dissolving silver bromide. And then finally, we took a little bit of the silver bromide precipitate and reacted it with concentrated ammonia. In the presence of concentrated ammonia, silver bromide will dissolve to form a clear solution. Keep in mind, dilute ammonia is not capable of dissolving silver bromide. It is concentrated ammonia that is capable of dissolving silver bromide as it forms a complex with the silver ions. So that is it for bromide ions identification test with silver nitrate. Now let's see how iodide ions react with the silver nitrate solution. So to introduce iodide ions into the solution, we will be using potassium iodide. So we will take a little bit of potassium iodide solution into this test tube. And then we will add a little bit of silver nitrate to this test tube to see what changes take place. As you can see, upon addition of a little bit of silver nitrate into potassium iodide solution, we are starting to form a slight yellow color precipitate. This precipitate is silver iodide. So let me give it a little swirl. You can see a yellow color precipitate forming. Now this yellow color is quite low in intensity. You will not be directly identifying it as yellow if you do not compare it with a white background. So at the end of this practical, I will compare all of the three colors of silver chloride, silver bromide and silver iodide separately, and I will show you the colors, how they compare against each other. But we have to know that silver iodide has a yellow, or sometimes it is described as a bright yellow precipitate. Now, as we did before, we will dilute this precipitate a little bit. Now it's suspended in water, right? So we'll take this solid suspension and transfer some of it into two other test tubes. After transferring it into two other test tubes, we will add a little bit of nitric acid into one of the test tubes to see if nitric acid is capable of dissolving the silver iodide precipitate that we have here. So let's add a little bit of nitric acid. As you can see, adding nitric acid into this precipitate did not bring about any change, as nitric acid cannot dissolve silver iodide that is formed. Then we will take another portion of the silver iodide precipitate we have and add a little bit of concentrated ammonia. So we will add a little bit of concentrated ammonia to see if it can dissolve this silver iodide precipitate that we have here. Now, in the previous two instances, as you added concentrated ammonia into silver bromide and as you added dilute ammonia into silver chloride, upon addition of these reagents, we saw an immediate change taking place. That is the dissolution of the solid. But once you add concentrated ammonia into silver iodide, you can see no change takes place. This is because concentrated ammonia and as well as dilute ammonia cannot dissolve the silver iodide precipitate that is formed. No longer how long you keep it aside for the reaction to take place, you will see that the reaction will not take place, as concentrated ammonia cannot dissolve silver iodide. So let's go through our observations one more time. As a summary, we initially took a little bit of potassium iodide solution, reacted it with silver nitrate and formed silver iodide precipitate, which is described as a bright yellow color precipitate. And then To a portion of it, we added a little bit of nitric acid. No change took place as nitric acid cannot dissolve silver iodide precipitate. And finally, we added concentrated ammonia into silver iodide precipitate. Again, no change took place upon addition of concentrated ammonia into silver iodide. So these are the observations that you will get when you are doing a confirmation test or identification test for iodide ions with the use of silver nitrate. Now, let's compare the colors of the precipitates of silver chloride, silver bromide, and silver iodide. To do that, like we did before, we will be now adding silver nitrate onto sodium chloride, sodium bromide, and potassium iodide. So first of all, let's take a small test tube and take a little bit of sodium chloride. And to it, we'll add a little bit of silver nitrate. As we mentioned before, we'll be forming a white color precipitate, which is silver chloride. So the purpose of this section of the practical is to compare the colors of the three precipitates. So we will leave silver chloride precipitate here and we'll move on to reacting sodium bromide with silver nitrate. To this sodium bromide solution, let's add a little bit of silver nitrate. We can see a pale yellow precipitate forming. So once you compare it against the silver chloride precipitate, we can see the slight yellow color of sodium bromide reacting with silver nitrate forming silver bromide. Right, so the silver bromide is slightly having a pale yellow color. So when you are comparing the two, you will be able to observe the two colors very clearly. Right, now let's move on to silver iodide. So if you take potassium iodide and react it with silver nitrate, if you take potassium iodide and react it with silver nitrate, you will be forming a yellow color precipitate. This is referred to as a yellow color precipitate. Now this is a yellow color precipitate of silver iodide. As a result of reacting potassium iodide with silver nitrate, we obtained silver iodide, we obtained silver iodide precipitate, which is described as a yellow color precipitate. I know it's difficult to observe this yellow color, but when you compare it against a silver chloride precipitate, you will be able to notice the color difference. Silver chloride is a white color precipitate. Compared against it is silver iodide, yellow color precipitate. So now this thing precipitates, since it's very fine, it is suspended in water. It looks as if it's a cream or yellow color solution. No, it's a yellow color precipitate suspended in water. So this is a suspension of the precipitate. So now when you have all three compared against each other, you will be able to see the slight color variations of the three precipitates. Silver chloride being white and silver bromide having a pale yellow color in the precipitate, and silver iodide having a yellow color precipitate. All right, everyone. So that is going to be the comparison of the three precipitates formed when chloride ions, bromide ions, and iodide ions are reacted with silver nitrate. So I hope you can see the colors separately. And now let's move on to the next step in our practical. Let's take a look at how sodium chloride, sodium bromide, and potassium iodide will react with lead nitrate. Now, our practical book tells us that we have to use lead or lead acetate, but instead we'll be going along with lead nitrate, because the purpose of using either of those solutions is to introduce lead ions into the medium. So we'll be using lead nitrate, which is water-soluble ionic compound. So it will be bringing in lead ions into the medium without any problem. And each of these salts or salt solutions, sodium chloride, sodium bromide, and potassium iodide, will bring in chloride ions, bromide ions, and iodide ions into the medium when you are doing the experiment. So without further ado, now we have labeled our test tubes because it will be easier for us to identify what solutions are in them when we have already labeled them. So to an already labeled test tube, I will be taking in a little bit of sodium chloride solution. Let's take a little bit more. And now to this sodium chloride solution, or solution that contains chloride ions, I will be adding a little bit of lead nitrate. Now please observe, students, upon addition of lead nitrate, we are seeing a precipitate being formed slowly. So this precipitate is lead chloride, a white color solid. Water insoluble white color solid lead chloride will be formed. PbCl2 is the formula. So you can see a nice white color precipitate forming and already accumulating at the bottom. So we'll give it a little swirl and then leave it aside and move on to bromide ions. We will take another test tube labeled bromide ions, and we will transfer some of the sodium bromide into this test tube. Now, students, I have a little bit of sodium bromide solution over here. In this solution, we have sodium ions and bromide ions. We are mainly carrying this test out for halides. So over here, the bromide ions that we have are the main focus. So if you add a little bit of lead nitrate into this, you will see the bromide ions that is present in this solution will react with the lead nitrate, more precisely the lead ions in the lead nitrate solution, and will form again a white color precipitate. It was a quite fast reaction. As soon as you added lead nitrate, you could see the formation of lead bromide. Lead bromide, PbBr2, is the formula, and it is a white color precipitate. Both lead chloride and lead bromide happens to be white color precipitates. And now let's move on to potassium iodide. Let's move on to potassium iodide. We'll take a little bit of potassium iodide solution over here. Now, In the test tube over here, we have a little bit of potassium iodide solution, which contains potassium ions and iodide ions. Our main focus here is the iodide ions. As we saw, iodide ions are added with lead nitrate. It will form lead iodide. Lead iodide is actually a very nice precipitate. A yellow color precipitate is formed instantly when you add lead nitrate into this. So let's give it a little shake. Now you can see the entire solution appears to be yellow. Do not be mistaken. This is not a yellow color solution that is formed. Instead, since the precipitate that is formed is quite fine in nature, it is dispersed in water, or we can say suspended in water, forming a suspension of the precipitate. So we will leave it aside to observe if it collects at the bottom. And now we actually have a small comparison that we can make. When you have chloride ions reacting with lead ions, we form lead chloride, which is a white color precipitate. When bromide ions react with lead ions, we formed lead bromide, again a white color precipitate. And when reacting iodide ions with lead ions, we form lead iodide, PbI2, which is a yellow color precipitate. Now, we want to see if these precipitates are soluble when we heat them after adding a little bit of water onto them. So let's separate some of these precipitates into a different test tube, and let's try to dissolve them by heating them. Now let's start mixing these precipitates again and separating half of it to a different test tube, because we will be trying to dissolve these precipitates by heating them with water. So let's take the lead chloride precipitate, which is a white color precipitate, and let's mix it a little bit like so. And now let's transfer some of it to a different test tube. We'll do the same to lead bromide as well. Right? This is lead bromide. Let's mix lead bromide a little bit and transfer some of this lead bromide into another test tube. And finally, we'll do the same with lead iodide as well. We'll take a little bit of lead, we'll take the lead iodide and mix it quite well and transfer some of the lead iodide suspension into a different test tube. Now that we have separated it into different test tubes, let's dilute them by adding a little bit of water. So to each of these test tubes, I'm going to be adding a little bit of water to dilute them further. I'm using a wash bottle to add a little bit of distilled water onto these three test tubes. Now students, you can see even after adding a little bit of water, the precipitates still prevail. Yeah, the precipitates still are there. They are still present as this is lead chloride, a white color precipitate. Upon addition of a little bit of water, lead bromide is still present as a white color precipitate. And lead iodide is still present as a yellow color precipitate. Now, what we are going to do is, we will be adding all of these into a water bath. What you see over here is a water bath. You can see a spirit burner set up with a tripod and wire mesh and a beaker full of water. So we will be heating this water bath with the use of our spirit burner. So as the water heats up, we will be transferring these 3 test tubes onto our water bath. And we will observe over time how these precipitates will dissolve in the hot water. So we will give it a few minutes and we'll come back and see whether the precipitates have dissolved or not. Now students, please observe how some of the precipitate that we initially had has started to dissolve when we were heating this test tube up. Right? So when the test tube was heated, some of the precipitate started to dissolve in that hot water. So this was the lead chloride suspension we had, right, or lead chloride solid we had, has now started to dissolve. You have lead bromide solid, which is almost completely dissolved by now, right? So still some of it remains. You can see when I shake it, it kind of starts to dissolve a little bit better. And if you observe our lead iodide solid, the solution has now started to kind of lose some of its color. That is due to most of the precipitate starting to dissolve. Now this color change is still not very clear, but if you leave it there for a little while longer, you will observe that all of the precipitate completely dissolves as you heat it up. So we'll give it a little bit more time, and once it's completely dissolved, we'll come back and observe the changes. Students, we are back after a while. Before we took a small break, what we did was we took a little bit of lead chloride, lead bromide, and lead iodide precipitates, and we transferred some of those precipitates into another set of test tubes, and then we added water onto those test tubes and we heated them for a while. Now we are going to be looking at the results. If you take the lead chloride precipitate has now completely dissolved in hot water. So for comparison, if I take lead chloride precipitate before heating it. You can see it was a white color precipitate. Now, after heating it with water, it has turned into a clear solution. So this is evidence that you can take lead chloride precipitate and dissolve it in hot water. Then we took a little bit of lead bromide, added a little bit of water, and we heated it for a while. So if you take a look at the results, you can see the lead bromide precipitate completely dissolved in hot water. And upon dissolving in hot water, it formed a clear solution. So this observation is evidence for the fact that lead bromide is soluble in hot water. And then we'll move on to lead iodide. Again, we took a little bit of lead iodide precipitate and we heated it with a little bit of water, and now you can see lead iodide precipitate completely dissolved in hot water and formed a clear solution. You do not see a yellow color in this hot solution because all of the lead iodide precipitate completely dissolved to form a clear lead iodide solution in hot water. So this is evidence that lead iodide precipitate can dissolve in hot water. So now, since we have shown that in hot water all the three halides of lead can actually dissolve, we will give it some time to cool down. We want to see upon cooling down whether these precipitates will be reformed. So we will wait for another few minutes and observe the formation of the precipitates of lead chloride, lead bromide, and lead iodide upon cooling these hot solutions. Students, you can see here when it comes to lead iodide hot solution, as it cools down, it starts to form lead iodide precipitate again. Earlier on, it was a clear lead iodide solution formed by dissolving the lead iodide in hot water. Now, when it is cooling down, you can very clearly see a yellow color lead iodide precipitate forming again. When it comes to lead bromide and lead chloride, it is somewhat slower in forming the precipitates, but as time passes by, those two will also form a white color precipitate. Now, we have allowed the solutions to cool down for 5 minutes. If you can see, there is a small precipitate starting to form when it comes to lead chloride. Right, lead chloride solution that was hot lead chloride solution is now starting to precipitate out solid lead chloride, which is white in color. So if I show you the precipitate that is being formed, I hope you can see needle-like white color precipitates being formed here. So if I let it stand for even a little bit longer, we can see the entire precipitate being formed and sedimenting at the bottom as a white color precipitate. So what you see here is upon cooling, the hot PbCl2 solution, which was a clear solution, when we cool it, we are forming PbCl2 solid, lead chloride, solid white color precipitate. And over here, we had clear solution of lead bromide, which was formed by heating lead bromide solid in hot water. And now we have allowed it to cool down for a while. So you can see when I mix it up, you can see again a white color precipitate that is being formed, which is lead bromide solid, PbBr2 solid. So upon cooling, lead bromide, hot solution, when you cool it, will be forming lead bromide solid. Over here, we have our lead iodide solution, which was a hot solution earlier on. Now it is cooling down. So as you can see, earlier on, this was a clear solution. When we heated lead iodide with some water, we saw that the yellow color lead iodide precipitate completely dissolved to form a clear solution. Now, this clear solution has turned a little bit yellow again due to the formation of lead iodide precipitate. Now, lead iodide has a glistening effect on it, right? If you are not sure whether the camera can capture it, the fine particles that are reforming upon cooling down, these fine lead iodide crystals has a small glistening effect, which gives it like a gold dust color. But this is lead iodide solid being formed when you cool down the lead iodide solution that was formed with hot water. So those are the observations when you take lead chloride, lead bromide, and lead iodide, and when you heat these precipitates, we saw all of those precipitates dissolved to form clear solutions, but upon cooling, they reform the solid precipitates, lead chloride and lead bromide, which are white in color, and lead iodide, which is yellow, a bright yellow in color. So that is a summary of chloride ions, bromide ions, and iodide ions reactions with lead ions. Now let's move on to the next step. Students, now let's talk about the chlorine water test for halides. In this test, we will be taking a look at how sodium chloride solution, sodium bromide solution, and potassium iodide solutions react in the presence of chlorine water. As you know, these halide ions will react with chlorine water except for sodium chloride, sodium bromide, and potassium iodide solutions. When they react with chlorine water, the halide ions will be displaced. For example, if you take sodium bromide, when sodium bromide reacts with chlorine water, Br minus ions will be displaced as bromine or Br2. If you take potassium iodide, the iodide ions in the potassium iodide solution will be displaced as I2 or iodine in the medium, right? So without further ado, let's move on to the chlorine test. In this test, we will be using carbon tetrachloride as the organic layer. So as you know, all of the bromine or Br2 and the I2 that is formed are non-polar. Non-polar substances are more soluble in non-polar solvents. So that is why we are using carbon tetrachloride, our carbonic layer or organic layer. Let's take a test tube and transfer small amount of sodium chloride. And we'll place it here. We'll take 3 test tubes and now we will transfer small amounts of each of the halide solutions first. This is the bromide ion solution. And we'll take the iodide ion solution as well. And now we have taken 3 test tubes, and onto those 3 test tubes we have taken the halide ion solutions. Now let's transfer small amounts of carbon tetrachloride CCl4, which is our organic solvent. Carbon tetrachloride, students, is a non-polar organic solvent which is denser than water. So what we have here is a sodium chloride solution. It's in aqueous medium. So when I add a little bit of carbon tetrachloride to this, I hope you can see this observation. The carbon tetrachloride sinks to the bottom. The reason for this is carbon tetrachloride, or CCl4, is denser than water. So it will sink to the bottom, and at the same time you can see clear layer separation. It will be present as 2 layers. This is due to the fact that the organic layer over here, which is non-polar carbon tetrachloride, do not dissolve in the polar aqueous layer. So now we have a small amount of carbon tetrachloride at the bottom and aqueous sodium chloride at the top. And then we'll do the same to the other 2 test tubes as well. To the sodium bromide solution, I will be adding a little bit of carbon tetrachloride as well. You can see again a clear layer separation, as well as the fact that carbon tetrachloride sinks to the bottom because all of these are aqueous solutions. So when you add carbon tetrachloride to any aqueous solution, we expect it to sink to the bottom because carbon tetrachloride is denser than water. Now what I'm holding right now is our potassium iodide aqueous solution, and onto that I have added a little bit of the organic solvent, which is carbon tetrachloride. Now students, we will be starting from potassium iodide and will be moving on to sodium bromide and sodium chloride, and we will be adding a little bit of chlorine water starting from potassium iodide. So let's take potassium iodide with carbon tetrachloride over here, and let's add a little bit of chlorine water. So as you know, chlorine in the presence of iodide ions will displace iodide ions and turn iodide ions into iodine, I2. As you can see instantly, when I start adding chlorine water, you can very clearly see the formation of a brown color solution over here. This is due to chlorine water reacting with potassium iodide and forming I2 or iodine. Now I2 is dissolved in the water layer. I haven't still mixed it up, and you can see due to dissolving I2 in water, there's a slight brown color present. So if I shake it a little bit, you can now see the brown color is evenly spread in the water layer. Still, it has not gone into the carbon tetrachloride layer, which is the organic layer. However, currently iodine is dissolved in the aqueous layer. Iodine, or I2, is a non-polar substance, And carbon tetrachloride at the bottom over here is also nonpolar. So as you know, likes dissolves likes, which means I2 should be dissolved more in the nonpolar carbon tetrachloride layer. So to do that, we have to first of all mix this mixture thoroughly. So let's do that now. Upon mixing it thoroughly, you can see that the organic solvent layer, which is the carbon tetrachloride layer, is turning purple. It has turned purple compared to how it was before. So this is due to iodine dissolving in the CCl4 layer. And if you keep shaking it for a while, and if you let it aside to stand for a while, you will see most of this color on the aqueous layer will decrease over time, and the intensity of the purple color on the carbon tetrachloride layer will increase. So the observation over here is the presence of a purple color in the CCl4 layer, which is evidence of the presence of I2 being formed upon addition of chlorine water. So this test is evidence that if you add chlorine water into iodide ion solution, if you add chlorine water into an iodide ion solution, the iodine or iodide ions will convert into iodine and will be displaced. And then if you add an organic layer like this, that iodine will dissolve in the organic layer due to its nonpolar nature, and you can observe the purple color like this. Now let's move on to sodium bromide solution. So we have sodium bromide solution. On the top layer over here is our aqueous sodium bromide layer, and at the bottom is our carbon tetrachloride layer. So to this, we are going to be adding a little bit of a chlorine water solution. So let's add a little bit of chlorine water. Now you can see, as soon as I add a little bit of chlorine water, the color of the top layer starts to change. This is due to the fact that when you add chlorine water, the bromide ions that is present in the medium gets displaced as bromine, or in other words, Br minus gets reduced to Br2. So Br2 in aqueous medium normally gives off a yellow-brown color, or in this case, it appears a little orange. So this orange color is present in the top layer. And then if you give it a little bit of a shake or swirl, you can see the color will go from the top layer to the bottom layer. Most of the color will transfer there, but the top layer will retain some color, but still we'll give it a shake and see. Now, after shaking it quite well, you can observe that the most of the color that was present on the top layer is no longer there. It has transferred onto the bottom layer. Bottom layer is our carbon tetrachloride. Carbon tetrachloride is nonpolar, as I mentioned before, and the bromine or Br2 that is formed is also nonpolar. So bromine dissolves in the nonpolar layer better than it dissolves in water. Water is a polar solvent. So bromine dissolves better in the nonpolar layer and turns that carbon tetrachloride nonpolar organic layer into an orange color. So the organic layer turning orange upon addition of chlorine water into a bromide ion solution and then shaking the solution well is evidence of bromine ions being present or bromide ions being present in the solution. So when you want to test for bromide ions, this is one test that can be done. And if the carbon tetrachloride layer, or instead of carbon tetrachloride, you can use chloroform as well. If the organic layer or non-polar organic layer turns an orange color, that is an indication of bromide ions being present in the aqueous layer. So as you can see, these are the observations when we add chlorine water into a bromide ion solution and then mixing it with carbon tetrachloride. Now, finally, we will be taking the sodium chloride aqueous solution that is coupled with carbon tetrachloride. So in this test tube, we have a layer of aqueous sodium chloride, which is clear, which is a clear solution. And we have at the bottom over here our carbon tetrachloride organic layer. Now we'll be adding a little bit of chlorine water onto the sodium chloride solution. Did you observe any changes? The answer to that would be no. The reason we will not see a change when we add chlorine water to a chloride ion solution is because chlorine will not, or Cl2 will not displace chloride ions because it's the ionic form of chlorine. So over here, you will not see any displacement or you will not see any color change happening just because we added a little bit of chlorine water. So when you do the chlorine water test to chloride ions, the observations would be no change upon addition of chlorine water to a chloride ion solution. So let's focus on the summary of this test. When we add chlorine water to a chloride ion solution, we observed no change. When we conducted the chlorine water test to a bromide ion solution, we saw that bromine was displaced, and when bromine gets dissolved in the organic layer or the nonpolar organic carbon tetrachloride layer, we can see that layer turning orange. This is an indication of the presence of bromine, Br2. And when we conducted the chlorine water test for iodide ion solution, we see upon addition of chlorine water, the aqueous layer turned brown, and then when we shake it well with the organic layer, which is the carbon tetrachloride layer, organic solvent layer, you will see the organic solvent will turn purple color. So this purple coloration indicates the formation of iodine, I2, and dissolving of iodine in the organic solvent layer will turn that solvent into a purple color. So these are the observations that are there when we conduct the chlorine water test. Let's move on to the test with concentrated sulfuric acid. Finally, we are moving on to the reactions that will take place when we react potassium iodide solid, sodium bromide solid, and sodium chloride solid with concentrated sulfuric acid. So now, first we'll take potassium iodide solid. Little bit of potassium iodide we'll take into a small boiling tube. And after taking small amount of potassium iodide solid into a boiling tube, let's add a little bit of concentrated sulfuric acid. As you can see, when we are adding concentrated sulfuric acid onto this potassium iodide solid, there was a purple color gas formed. And you can see that interior walls of this is also turning purple due to that gas being formed. So this is due to the release of iodine or I2 gas. So I2 gas is purple in color. When you react a good oxidizing agent like concentrated sulfuric acid with potassium iodide, potassium iodide or iodide ions in the potassium iodide will be converted into I2 and form I2 gas, which is evolving here as a purple color gas. In the previous experiment we did, we added concentrated sulfuric acid to potassium iodide solid, and we saw a purple color gas, which is iodine gas, I2 gas being formed. Normally, it is not advisable to have a lot of gases roaming around in a lab atmosphere. So we had to remove the sample that we did the experiment with in order to make sure the space that we do these experiments are kept safe. So in the future also, when we do the experiments for sodium bromide and sodium chloride, we will be removing those samples right after the practical is done, just to make sure the lab environment that we have here is kept safe. So let's move on to our second halide ion, which is sodium bromide. We'll take a little bit of the sodium bromide solid and we'll add it to a boiling tube like this. And now let's add a little bit of concentrated sulfuric acid to this sodium bromide solid. Let me take a little bit of concentrated sulfuric acid and add a little bit of that into the sodium bromide solid. You can see effervescence being formed, and it is orange in color. I'm not sure whether the camera can capture the fume being a little bit orange in color. You can see the interior walls of the boiling tube also is turning a little bit orange. This is due to the formation of bromine gas. In the presence of concentrated sulfuric acid, sodium bromide or the bromide ions in sodium bromide will be converted into bromine gas, which now is evolving as a orange color or red-brown color gas. Now we'll have to remove this sample from the lab. Finally, let's move on to sodium chloride. So concentrated sulfuric acid is a good oxidizing agent. Let's see what it does to sodium chloride. So let's take a boiling tube and add a little bit of sodium chloride onto that. It will be easier to add it like this at times. And before I add sulfuric acid, I would like to mention the reaction that is happening here. So once you add concentrated sulfuric acid onto sodium chloride, the chloride ions will not convert into chlorine gas. Instead, it will form HCl gas that appears as a misty fume. So the HCl gas can be tested with blue litmus paper, and at the same time we can use pH paper to identify how acidic this gas is. So here in this petri dish we have blue litmus paper as well as pH paper. To use them, we have to make sure that these litmus papers are wetted with a little bit of distilled water. The reason for us to add a little bit of water onto these papers before we expose them to the gas is to make sure that the gas will adhere to these papers and dissolve in the water that is present on the paper and can show us a color change by having those gases coming into contact with the paper properly. So now let's add some concentrated sulfuric acid onto our sodium chloride solid. Now, as I mentioned earlier, upon addition of sodium chloride, you will see a gas evolving. Now, this gas is going to be a white color gas, or we call it a misty fume. You wouldn't necessarily have a characteristic color to it, so you cannot identify chloride ions by just adding sulfuric acid. But we can identify the gas that is evolving with the help of litmus paper. As you can see, when I hold a wet litmus paper onto this gas, the wet blue litmus paper is turning red. This is an indication of the gas being acidic. Now let's try using a pH paper to determine the acidity of the gas. Immediately, when you hold the pH paper, you can see the pH paper is turning red. Red indicates high acidity. However, after a while, we will compare it against the pH scale that is provided with the pH paper book. Right, everyone? Like I mentioned, upon addition of sulfuric acid to sodium chloride, we produced HCl gas, and we confirmed it with the use of litmus paper. Blue litmus paper turned red, and pH paper turned also into a red color. So now if you compare pH paper guide that is given over here, it's a bright red color, which indicates the pH of the gas that is released is between 1 and 3. So this is a highly acidic gas that is produced. If I show it to you over here, acidic gas that is produced, which indicates it is HCl that was released when concentrated sulfuric acid was added onto a sodium chloride solid. That brings us to the end of this practical 13. In the last section of the practical, we looked at how sodium chloride, sodium bromide, and potassium iodide reacts with concentrated sulfuric acid. To summarize, potassium iodide, when added with concentrated sulfuric acid, we saw the evolution of a purple color gas, which is I2. And then when we added concentrated sulfuric acid to sodium bromide, we saw that orange color effervescence being formed, indicating the presence of bromine gas or the formation of bromine gas, which is an orange color gas. Finally, when we added concentrated sulfuric acid to sodium chloride, we saw that a white color gas was formed, or we call it misty fumes, that is acidic in nature. We tested its acidity with pH paper as well as blue litmus paper. So we confirmed the gas that is produced is acidic. So the gas that was produced upon addition of concentrated sulfuric acid was HCl. We cannot identify sodium chloride by adding concentrated sulfuric acid, as the gas that is evolved is going to be colorless. But the other two halides, bromide ions and iodide ions, can be identified by the color of the gas that is evolved. If a purple color gas evolves, that solution would have contained iodide ions. If a brown color or maybe orange color gas is evolved, that indicates the presence of iodide ions. So that will be all for this practical. We will be moving on to the important theory parts and questions related to this practical in our next session.